This is part 2 of the Module 9 lecture, and this is the first part that focuses on comparing the variances of two independent populations. And in looking at the diagram that we saw in the first recording, so in here we're going to compare two independent populations, but we want to compare their variances. So this is the first part that we're going to be looking at, comparing the variances of two independent populations. Typically these tests arise from the need to demonstrate that the variability of a process has been reduced after some improvement. Generally we want the variance before being larger than the variance after, because after an improvement we expect the variance to be smaller. Another need that arises is when we want to select the correct method to compare the means of two independent populations. In order to select the correct method, we need to determine if the variances are equal or not. So if they're equal, what you have is two identical distributions with the only difference being their location, that is their means. Or you may have a situation where you have two distributions with different variances and different locations. All right, so this is what we want to do, compare two variances from two independent populations. All right, to do this, well, we need to use a different statistic, and then this is called the F statistic. And as you can see, is defined as the ratio of the sample variance to the population variance of the first distribution to the ratio of the second sample variance and population variance of the second distributions. By doing the algebraic rearrangement, you can see that this is identical as the ratio of the sample variances of the two populations divided by the ratio of the two population variances. Now, as long as the samples N1 and N2 are independently drawn from two normally distributed populations, this F statistic follows a F distribution, which now is classified with 2 degrees of freedom, what we call the numerator degrees of freedom, because this standard deviation S1 squared is in the numerator of this ratio. So this degrees of freedom of the numerator goes with the sample for the first sample variance. And the denominator degrees of freedom, now it goes with the sample variance in the denominator of this ratio. So it's very important to know which variance is on top and which variance is at the bottom, because then we're going to use the degrees of freedom correspondingly. All right, so an F probability distribution is the F values are always positive because it's the ratio of two positive things. So the F distribution is positively skewed. There cannot be values below 0. And is determined by two parameters, the degrees of freedom in the numerator and the degrees of freedom in the denominator. And here this graph is showing you multiple F distributions for different sets of degrees of freedom. So, as you can imagine, there is an infinite number of F distributions, one for each pair of degrees of freedom. Now, Table 7, that's in the back of the book, and I will post that table in the probability tables for this module. Then you see that this table shows F values that we are going to designate as F sub A, with the degrees of freedom in the numerator and the degrees of freedom in the denominator for probabilities to the right for some probability A. So table 7 for a particular probability A is going to give you this F value right here, the one at the top. And of course, to select the right F distribution, you need to know the degrees of freedom in the numerator and the degrees of freedom in the denominator. All right, so if the test requires that you need the F value on the lower end of the distribution for the same probability A, we call this F value, used to distinguish it from this one, 1 minus A, the F for the numerator and the f for the denominator. And we distinguish it as 1 minus a because since this distribution is not symmetric, these two values are not equal. So this distribution, remember, is not symmetric. So the lower value for the same probability is not the same value, the same upper value for the same probability. So we need to calculate them separately. All right, here's an example. They're asking us to find the lower f value from an f distribution with a probability a of 0.025, with the numerator degrees of freedom of 4 and the denominator degrees of freedom of 9. All right, so you need to go to your table 4, and there are 4 sheets to that table, and then you find the sheet where at the right top of the table you see this diagram, and you're looking for this number 0.025. That's the probability A that I'm using here. So that's there. So once you find that sheet, then you look at the top, you look for the degrees of freedom of the numerator, in this case 4. Well, you locate that column. And then on the rows, you look for the degrees of freedom of the denominator, in this case 9. So at the intersection of these two, of this column and this row, you find the f value to the right on the right side for this probability. But remember, here they're asking us for the lower value. So now what we're going to do is use the upper value that we just found on the table, and we need to calculate the lower value. So this will be just the inverse of the upper value, and that result will give us the value on the lower end for the same probability. So that's how we use the F table. All right, in the next section, we'll talk about now using this hypothesis test process to compare the two variances from two independent populations.